Welcome back to Astronomy. In the next 3 chapters, we'll look at the entire life cycle of stars. So this video, chapter 16, will look at how stars are born. Chapter 17 will be the life of stars. And chapter 18, titled The Bizarre Stellar Graveyard, will look at what happens after stars cease to become stars. So let's look at where do stars form. They form in star-forming clouds that are otherwise known as stellar nurseries. Stars form in dark clouds of dusty gas in interstellar space. And remember, the word interstellar simply means between the stars. The gas between the stars is called the interstellar medium. Here is a molecular cloud. This is actually called the Horsehead Nebula. Most of the matter in star-forming clouds is in the form of molecules, for example, molecular hydrogen and carbon monoxide. These molecular clouds are very cold. They have a temperature of only between about 10 and 30 Kelvin and a density of about 300 molecules per cubic centimeter. As far as interstellar medium goes, that is fairly dense, although if you compare it with the density of Earth's atmosphere, the atmosphere in the room where you're sitting is probably about 10 to the 19th molecules per cubic centimeter. And so in comparison, this is very empty, these molecular clouds, yet still compared to the rest of the galaxy, they are considered dense clouds. In this picture, you can see on the left a visible light image of the nebula. And on the right, you can see a radio wave image of it. And these radio waves show particularly carbon monoxide molecules. This is Barnard 68. It looks like a dark void in space, as if there's something missing from the picture. And actually, it is a cloud of gas and dust, and the dust is blocking the light from the stars that are behind it. Stars viewed through the edges of the cloud look redder because the dust blocks the shorter wavelength blue light more effectively than longer wavelength red light. So if you look around the perimeter, you can see the stars have dimmed and there's more reddishness to them. Now, if we look at the same cloud through infrared, the infrared light travels through the dust cloud, so the cloud, it blocks it, reddens it a little, but it doesn't block it. So long wavelength infrared light passes through a cloud more easily than visible light. Observations of infrared light reveal stars on the other side of the cloud. And here we can see side by side pictures of Barnard 68. On the left, it's looking at with visible light, and on the right with infrared light. Why do stars form? A star starts as a very large cloud, such as some of the examples I showed earlier in this video. And what this image represents is a computer model, a simulation. So a large cloud, this particular simulation is a typical cloud about 1.2 light years across. And it contains about 50 solar masses worth of gas. Now, the random motions of different sections of the cloud cause it to become lumpy. And in this simulation, each lump of the cloud in which gravity can overcome pressure can go on to become a star. A large cloud can make a whole cluster of stars. So when we look back at those stellar nurseries like Barnard 68 or the Horsehead Nebula, a cloud like that might go on to become one star, or if it has this lumpiness to it, it might go on to be many stars, which would form in a cluster. Here is one such cluster of many stars that formed a long time ago. And sometimes they're more tightly bound to each other gravitationally than others. If they're tightly bound to each other, It's a globular cluster if they're not so tightly bound. It's called an open cluster. As an individual star forms, remember back to chapter 8 when we studied the formation of our solar system, and I showed that when we look out into the galaxy, we see this happening, other stars being formed. There is flattening. Collisions between particles in the cloud cause it to flatten into a disk. And you've seen this picture before in my earlier videos. This is a picture of a protostar in the middle, and these dark lanes suggest planetary formation. Collisions between gas particles in the cloud gradually reduce the random motions. Collisions between gas particles also reduce up and down motions. And so the spinning cloud flattens as it shrinks. And I encourage you to go back to about chapter 8 in this class and take another look at the video Creation of the Solar System. So as I've shown so far, sometimes a large cloud of gas will become an individual star, as what happened to our sun. Sometimes it becomes many, many stars, sometimes as many as a million or more stars. And it just depends how much mass there is in that cloud of gas. Let's now think about one particular star. What happens as it goes from being a cloud of gas to being a star on the main sequence? We're going to look at the life track. A life track of a star illustrates the star's surface temperature and luminosity at different moments in time. You can see how it's starting way down and to the right of the Hertzsprung-Russell diagram. Now think about what that positioning means. To the right, if you follow the horizontal axis, on the left is hot, O, B, A, F, G, K, M. You go off the chart to the right, and we're looking at very, very cold, because remember, these clouds of gas, they start off between about 10 and 30 Kelvin, very cold. Down on the chart means low in luminosity, meaning very dim. So we'll look at step 1. As the cloud shrinks and it gets hotter in the center, luminosity and temperature grow as the matter collects into a protostar. So luminosity grows, meaning it's going higher up on the chart, and it's moving to the left, meaning it's getting warmer. As the star continues to shrink gravitationally and more stellar matter or more matter from the cloud is falling onto the star, it gets hotter and hotter, so the core temperature continues to rise until, going between steps 2, 3, and 4, it settles on the main sequence. The star begins nuclear fusion. And where it settles on the main sequence is going to depend on its mass. So if it has a lot of mass, maybe 8 or 10 solar masses, it's going to be brighter and it's going to be hotter, so it'll settle somewhere up here. If, like the majority of stars, it doesn't have that much mass, maybe only a tenth of a solar mass, it's not going to be as bright, it's not going to be as hot, so it'll be here among the red stars. This star right here at position 4, this represents what happened to our sun. It had the right amount of mass to become 1 solar luminosity and a G-type star. Computer models show that the sun required about 30 million years to go from a protostar, which is way off down to the right, to become a main sequence star, so about 30 million years. And again, that is computer models that do that. So the astronomers write a program that takes into account the laws of physics, the laws of gravity, nuclear fusion, all those things, and see how long does it take in the simulation. And of course, the simulation is run sped up, and typically about 30 million years. Higher mass stars form faster. So a star of about 15 solar masses, only about 60,000 years. The low mass stars form more slowly, maybe as many as 150 million years. Let's talk about how massive a newborn star can be. Our goals for learning: what is the smallest mass a newborn star can have? What is the largest mass a newborn star can have? And what are the typical masses of newborn stars? We'll start with what is the smallest mass a newborn star can have. As the star heats up, as the material from the cloud gets gravitationally pulled onto it, it needs to get up to a certain temperature in order for there to be nuclear fusion. Fusion will not begin in a contracting cloud if some electron degeneracy pressure stops contraction before the core temperature rises above 10 million Kelvin. Electron degeneracy pressure halts the contraction of objects with less than 0.08 solar masses. That means 8% of the sun's mass before the core temperature becomes hot enough for sustained fusion. So electron degeneracy pressure, you can think of that as if you contract the stellar material tight enough into a dense enough ball, the electrons start pushing against each other. It's like crowding 100 people into a medium-sized room. There's a point at which they're going to push against each other and not allow any more to come in. So the electrons pushing against each other will just stop the contraction of the core. If it hasn't yet reached 10 million Kelvin, which is necessary for nuclear fusion, then it just will not become a star. It will be a dense ball of hydrogen and helium. It'll be very hot, but not hot enough for nuclear fusion. Star-like objects not mass enough to start fusion are called brown dwarfs. This is a painting of a brown dwarf. It looks kind of like Jupiter, and when you think about what Jupiter is a ball of hydrogen and helium gas. The sun is also a ball of hydrogen and helium gas, but they are very different entities. And the main difference is that the sun is hot enough to have nuclear fusion in its core. Jupiter is not. The straddling the line between gas giants and planets are brown dwarfs. They can have some sparks of nuclear fusion going on inside them, but it's not sustained nuclear fusion. It's just not massive enough to create that temperature. So this is the minimum mass of any star, 0.08 solar masses. By the way, the sun happens to be 1,000 times more massive than Jupiter. So sometimes when we're describing brown dwarfs, we give them not in solar masses, but in Jupiter masses. And so 0.08 solar masses is equal to 80 Jupiter masses. A brown dwarf emits infrared light because of heat left over from its contraction. Its luminosity gradually declines with time as it loses thermal energy. For brown dwarfs, which are these failed stars, these crosses between planets and stars, the masses of brown dwarfs are between 13 and 80 Jupiter masses, which is between 0.013 and 0.08 solar masses. The mass is too low to sustain core fusion of hydrogen 1 into helium. So brown dwarfs are not stars. However, they are star-like objects, just on the cool end of the spectrum. And so astronomers have found it convenient to list them by spectral type. So they invented new spectral types when astronomers discovered brown dwarfs. And so it's important to note that even though spectral types officially refer to stars, they give these spectral types to brown dwarfs anyway, even though they're not stars. So we add on to the familiar spectral types O, B, A, F, G, K, M, and we add on L, T, and Y. So the brown dwarfs that are the hottest brown dwarfs that are not quite M-type stars are L-type brown dwarfs. Cooler than that are T-type brown dwarfs, and cooler than that are Y-type brown dwarfs. So we've talked about what is the smallest mass a star can have, 0.08 solar masses, Anything smaller than that is going to be a brown dwarf. What about what is the greatest mass a newborn star can have? Photons exert a slight amount of pressure when they strike matter. We've seen that with the tails of comets. When light comes, radiation comes from the sun, it blows the comet tail in the direction away from the sun. Very massive stars are so luminous that the collective pressure of photons drives their matter into space. So if a star is pushing the limits of how massive stars can be, the pressure from the radiation it puts out will actually drive the stellar matter away, and it can blow the star up. As we think about what is the upper limit on a star's mass, computer models of stars suggest that radiation pressure limits how massive a star can be without blowing itself apart. The maximum mass is thought to be around 150 solar masses, but new observations indicate some may be even larger. So this is what computer simulation shows, something around 150 solar masses, but there is a great plus or minus, a great uncertainty in that. It is believed that we've possibly discovered a star that's as much as 200 solar masses. So we don't know exactly what the highest mass of a star can be. We do know, however, that if it gets around this limit, it's going to blow itself apart before it even forms. This chart shows the maximum and minimum of what stars can be. On the upper end of the main sequence, stars more massive than 150 solar masses would blow apart. Stars less massive than 0.08 solar masses cannot sustain nuclear fusion. So as we think about what are the typical masses of newborn stars, we've already established what the limits are, but typically, what is a star's mass when it's first born? And the breakdown goes like this. If you think the illustrator here made these different categories. So for every one star that is between 10 and 150 solar masses, there are going to be 10 stars that are between 2 and 10 solar masses. There are going to be 50 stars that are between half and 2 solar masses. So this would include the G stars that the sun is a part of. And there are going to be 200 stars that are less than half of a solar mass. So you can see that by far the majority of stars born are less than half of a solar mass. They're going to be those M stars and K stars, those reds and oranges. We can look at this chart by this breakdown. In any given cluster of stars, any given population of newly born stars, 77% are going to be red and orange, those K and M stars. 19% are going to be the whitish and yellow stars. Think of those as F and G stars. Only 4% are going to be greater than 2 solar masses. That means intermediate stars or high mass stars. And in chapter 17, I'll define that breakdown between low, intermediate, and high mass stars. And only 0.4% are going to be the very highest mass stars, greater than 10 solar masses. That is the end of chapter 16 on the birth of stars. In chapter 17, we'll look at the life cycle of stars. Have a great day.